For my demonstration, I will be setting fire to a towel, but as you will see shortly, the towel itself will not be burnt. To do this demo, you mix 50 milliliters of isopropyl alcohol and 50 milliliters of water in a container. Then place your towel in and make sure it's soaked through. Squeeze out any excess solution and using tongs, hold the towel over the Bunsen burner to catch fire. Make sure to hold it away from your body to be safe. When the isopropyl alcohol all burns off and the flame dies out, you will see the towel isn't burnt. We just saw this towel go up in flames. How can it be that there are almost no burn marks on it? For one, the specific heat of water is fairly high. That means that it takes a lot of energy for water to raise 1 degree Celsius. Before the towel can be burned, the water must reach a high enough temperature for it to all be evaporated off. If you have enough water in your solution, this won't happen before the isopropyl alcohol stops combusting and your towel won't burn. Another thing to consider is that though there is heat going into the water and the towel, there's also a lot of heat being lost to the surroundings. We will see just how much heat is lost in our calculations. First, let's find the standard change in enthalpy of the combustion reaction of isopropyl alcohol, using the enthalpies of formation. When we subtract the enthalpies of formation of products from the enthalpies of formation of reactants, we get a change in enthalpy of negative 1961.2 kilojoules per mole. Note that this number is negative. This means the reaction is exothermic, so it releases energy. We want to find out just how much energy is released, then subtract the energy that water is absorbing to see how much energy is released into the surroundings. First, we find the moles of isopropyl alcohol that are being combusted by understanding that if we start at 100 milliliters and use up 26 milliliters, that means 13 milliliters of the 70% isopropyl alcohol are being used. Of those 13 milliliters of the 70% isopropyl alcohol, we can figure out how much of that is moles of isopropyl alcohol. Multiplying the moles by the standard change in enthalpy of the reaction gives us the amount of heat that was released when the isopropyl alcohol was burned. In this case, it's 233.40 kilojoules. By finding the mass of the water that we used, which is 16.9 grams, and then plugging that mass in and the change in temperature into our Q equals ms delta T equation, we can see how much heat the water absorbed, which was 1.2 kilojoules, not very much. This means that 232.2 kilojoules were not absorbed by the water and were released into the surroundings. That is 99.48% of the heat produced. To summarize, the reason that the burning towel doesn't end up charred at the end is because a lot of that heat is released into the surroundings. The heat that isn't released into the surroundings is absorbed by the water, and thanks to the high specific heat of water, not all of the water evaporates, preventing the towel from charring. Thank you for watching, and remember, if you're going to do an experiment like this at home, please conduct it in a safe manner.